Welcome everybody to our discussion on our Unit 6 seminar topic, which is the one-way ANOVA. We're going to continue doing hypothesis testing, and from our last unit, Unit 5, you saw that we were doing t-tests for means, right? And we had three types of t-tests. We had a t-test where we had just one mean that we were comparing to a number. So that means we had one sample of data. We were going to take the average of that sample and we were going to compare it to some number, whatever number we wanted. Then we had a t-test for two independent means, and it was very similar to doing it for one mean because in one mean, you took the average of that sample and you compared it to a number. Well, when you have two independent means, you have two samples, and you take the mean of both of those samples, and then you compare those two numbers. So you can see how, if you think of, sample one, group one being the same thing as the first example, you take the average of that group and you compare it to a number. Well, that number just happens to be the average of the second group, right? So in essence, it's pretty much the same test. It's just with two groups instead of one. And then the third one, which is the different one, is when we're doing a t-test for paired differences in means. It's called paired samples t-test usually. And this is where either you have two groups that are linked, so sometimes we'll have like siblings and we'll look at test scores for siblings or test scores for spouses, that kind of thing. But oftentimes, instead of two groups that are linked, it's one group that's been tested twice. So you have a pre-test and a post-test. And then you're looking at the differences between all of those individual scores. So you're not just taking the average of all of the pre-test scores and the average of all the post-test scores and looking at the difference between those two averages, because that would be too similar to just doing the two tests for independent means thing. Instead, you take each individual person and you calculate the difference between their pre and post. And then you're going to look at the average of all those differences. And we normally take the post score and subtract the pre-score from it, because in that way, if you get a positive difference, it tells you their scores went up from pre to post, right? If you subtract it in the other direction, then everything would be counterintuitive. And so you can see that our hypotheses are slightly different. Right here we have mu just equal to a constant or not equal to a constant. Right here we have mu1 equal to mu2 or mu1 not equal to mu2. And then here we have the mu of the differences, right? So the average of the differences, we set that equal to 0, basically saying that there was no real change from test 1 to test 2 or pre to post. And then there is a difference. Now remember, these don't always have to be not equals. We could also do one-tailed tests, and we can make these, either greater thans or less thans. Okay, ANOVA testing, it stands for an analysis of variance, and it's a big fancy way of saying we're now going to do the exact same thing as a t-test for two independent samples, but we're going to do it when we have more than two groups, right? So a t-test for two independent samples is actually in reality just a special case of the ANOVA test where you only have two groups. But it's done so commonly that we just think of it as a t-test. But you could also just do it as an ANOVA with two groups. Those two things are literally identical. So if you have two groups and you ran a one-way ANOVA on two groups, you would get the exact same results as if you just ran a t-test for two independent samples. So all an ANOVA does is it allows you to do that same kind of comparison, but now for more than two groups. So anytime you have three or more groups, you just have to do an ANOVA. And just think of it as a t-test on steroids, right? It's still looking for differences between groups. It's just looking for differences amongst three or more groups. Now, the variable that you calculate means for is considered dependent, and it's quantitative. The variable used for splitting the groups into categories or groups is considered the independent variable, and it's categorical. So for instance, you could look at IQ scores for freshmen, sophomore, juniors, and seniors at a college, right? So the dependent variable would be quantitative, and it would be IQ scores. And then the independent variable would be categorical, and it would be, year in school, whether you're a freshman, sophomore, junior, senior. You could do the same thing with, you could look at, yearly salaries for people who are registered to vote Republican, Democrat, Independent, Green Party, on whatever else there might be, right? So for 5 different categories. So the categorical variable would be the independent variable would be the categorical variable that basically says, your voting affiliation. And then the dependent variable would be your yearly salary. Okay? So that's how these things work. You're just going to group things into various groups, and then you're going to take averages of those groups, and then you're going to check to see if there's any differences amongst them. The null is always that all of the groups have identical means, right? And you do mu's to indicate that all of the populations, not your samples, all of the populations have the same mean. And then the alternative, you have to actually write it out in English. It's too complicated to try and write it with symbols, because the alternative is just at least one group differs from another, right? Or basically the means are not all equal. So when you say the means are not equal, it's basically saying that at least one pair of population means is significantly different. Now you could have more than one pair, right? They could all be different, or there could be, 3 of them that are different, but it just means at least one pair is different. And by one pair, it just means that one mean has to be at least different from one other mean. And that's it. So that's what we're testing for. So for the mean depression score versus income level, the example that I kind of glossed over, but back here, right? Does mean depression score depend on income level, where income level can be 1 for low, 2 for medium, and 3 for high. So you can see there's your grouping variable. Your categorical variable is your income level, and then the depression score is your quantitative, and you're going to look at those 3 things. So for this, the HO would be that the mean depression score for all 3 are the same, right? So income level 1 equals income level 2 equals income level 3, and then the alternative is just some pair of mean depression scores are not equal, or some pair is not equal. So oftentimes we'll write it in symbols, mu1 equals mu2 equals mu3, and then you define what the mu's are, right, for income level 1, da da da. And then you could do this. Since there's only 3 of them, there's only going to be 3 pairs. 1 doesn't equal 2, right? 1 doesn't equal 3, or 2 doesn't equal 3, right? That's the only way to do it. So you could do that, or you could just say at least one pair is different. And that's why those are ors and not ands, because it's at least one, right? They don't all have to differ. And when you get more and more groups, you can see that this gets more and more tedious to write this all out. So oftentimes it's easier to just do it. Oftentimes there's a mixture, right? You don't do all verbal and all symbolic. Usually you'll always do this for the null, because that's easy. And then you'll almost always do this or something equivalent to it for the alternative. Okay, let's look at an example, right, where we've got these exercise hours, all these different qualitative things, and then how many hours they exercise, and then a bunch of other stuff. The research question: does average time spent exercising depend upon the class year? So basically this one, right? Whether they're freshman, sophomore, so on and so forth. So your dependent variable is your hours per week, quantitative of exercise. The independent variable is the year that you're in school, right? So that's categorical. So here's your 4 things, right? Because there's only 4 things. You can be freshman, sophomore, junior, senior. We're obviously going to discount or ignore graduate students. And then some pair of means is significantly different, right? So this is what I was saying about how you do the null with symbols and the alternative with words. Okay, when we ask, do the population means differ significantly, we're asking about how much they vary. Remember, that's the whole idea of hypothesis tests, is we're not just looking for a difference, we're looking for a difference that is significant, right? Statistically significant differences. So ANOVA testing is based on that same idea, and it's analyzing variances associated with those population means. And 2 ways in which populations can vary is within groups or between groups. Okay, so if we go back to the exercise example, we can talk about how to do it. So let's look at the distribution of exercise hours for each class in stat key. So you've got the one quantitative and one categorical variable thing there. So you click there and then you choose those two things. And then you can run some summary stats on them and see what's going on. And you can, kind of visually start to see if there's big differences in these variables. Then you can also look at the summaries and see, are there big differences? Like look at how small this mean is and how big this one is. There's going to be a significant difference between those two means. Whereas, these two are almost identical, and then there's not a huge difference from 10 to 12, right? So there's not going to be any difference between those. And there's not a huge difference from 7 to 10. There might be a significant one from 7 to 12, right? So it all depends once we run the data. So again, we have to figure out, what significant means. And again, I would point out just looking at the numbers rather than looking at the graphs. I don't think the graphs help that much. Now, two types of variation we talked about: variation among exercise hours for a class, which is within group variation, and then variation among class means, that's between group variation. So, how do we calculate that? Well, this is how you would do it by hand. Who in their right mind would ever want to do that by hand? It's much easier to do it with technology. Excel does it. It's very, very simple. So the first thing you have to do is you have to sort your data, because you're going to need to put all the groups in separate columns, right? So we've got all of the exercise numbers are just in one column. So if we sort by year in school, we can then take all of the ones, right, and put that in one column and call it like freshman exercise, and then scroll down to where the twos start, and then copy and paste all those and make it, soph exercise for sophomore exercise, and so on and so forth. So basically this is what it looks like once you copy and paste all of those exercise data values into their own columns based on year in school. And you can see that they're not the same, and that's okay. They don't have to be the same. And then you go to the data analysis tool pack and you choose ANOVA single factor. We're doing a single factor ANOVA. Single factor just means that your data is only separated, right, grouped by one single factor. And the one single factor we used to split up this data was the year they were in school. So that was the single factor we used to split up the exercise data. And then it's going to ask for the input range. So you're going to want to highlight all four columns and then say they're grouped by columns. And then if you have labels and you highlight, the whole thing like they did here, right? They just basically highlighted A through D, the whole column. Then you have to let them know there's labels in the first row. Then you choose where you want your output to be, right? I like to usually put it in the same sheet just so I don't have to go back and forth, look at my data, look at my results. But you can put it in a new worksheet or a new workbook, whatever you want. Hit OK. And then you're going to get something that looks like this if you were using this data. So first you're going to get basically summary statistics for your groups, right? So here are your four groups. Here's the count, right? Your N, how many is in each. Here's if you sum them all up. Then here's your averages. Obviously, if you took 270 divided by 22, you get this number, right? 197 divided by 18, you get that number, so on and so forth. And then the variance, remember the variance is just the square of the standard deviation. So you can see that this group varies a lot, this group varies a lot, and they're kind of similar. This group doesn't vary much at all, and this group is, it's getting close to a lot. So we can tell that this group's variance is going to differ a lot. We also see that their mean varies a lot. Okay, and then the ANOVA output is what really matters, is we want to know if there's a difference between the groups, not within the groups. Within the groups just tells us what's happening with these variances. We want to know if there's a difference in the means, right? So we're looking at differences between the groups. And so that's where we get a degree of freedom of 3, because there's 4 groups. So it's always n-1 for degrees of freedom. The F is our test statistic. Remember, we always have a test statistic. When we run in T-test, we got a T-stat. When we run Z-test, we get a Z-stat. When we run ANOVAs, we get an F stat, because this lives on the F distribution. It's just the name given for the shape of the distribution. T's are bell curves, right? Z's are bell curves. F's are not. They're asymmetrical. They're not symmetrical like a bell curve. So that would be your test statistic. This would be your p-value. And then the F critical it gives you, because on the previous thing, if you tell it what your alpha is, it will tell you what your critical value is. So if you set alpha to 1%, you're going to get a different critical value, right? These two won't change depending on alpha, only the critical will. So if you wanted to compare your test statistic to your critical value, you could also do that. But the easiest thing is just look at your p-value. You go, well, gosh, that's 26%. So there's no difference, right? So even though this was hugely different from 12, it wasn't different enough to make it significant. So when we have an alpha level of 0.5 and we get a p-value of 26, right, we can tell them what our test statistic is, the 1.37 blah, blah, blah. We can tell them what the p-value is, that, and then our conclusion is fail to reject, which means there is not a statistically significant difference between any pairs of groups, right, any pairs, right? So even though there seems to be a big difference between year 3 and year 1, it wasn't statistically significantly big enough to be able to reject. So that's how it works. It's just that simple. Now, what if we had rejected it? Well, if we had rejected it, then we'd want to figure out which of these pairs are different. And that's where you have to run post hoc tests. So if you do not reject, you're done. You don't have to do anything because none of the means are different. But if you do reject, you have two options. You can look at graphs and guess, not really a good idea, or you can do additional testing, post hoc analyses, to determine which pairs of group means are significantly different. The most popular is the two-key test. Vassrstats.com can do that. You can see the live binder will show you how to do that. And there's a video on how to do post hoc analysis. And then you can also do it by confidence intervals, and you can look that up in the book. But really, the two-key test is the most commonly way of doing post hoc. So just run the two-key test, and you can do that with Vassrstats.com. It's free and it's easy. Go watch the video that's in the live binder, and it'll show you how to do it. Okay, this would be if you want to do it with graphs, which I don't recommend. Just go do the two-key thing. So here's what you're going to get when you run a two-key test. You're going to get a display like this, and it basically does all the pairs, right? So it does group 1 versus group 2, group 1 versus group 3, group 1 versus group 4, then it moves on to group 2. And it doesn't do 2 versus 1 because it already did 1 versus 2 up here, right? And order doesn't matter. So it's going to go 2 versus 3, 2 versus 4, then it's going to move to 3, and again, it's not going to do 3 versus 1 or 3 versus 2 because we've already done that, so the only one that's left is 3 versus 4. So these are all your pairwise, and it just tells you if they're significant or not. It says these aren't, but these 3 are. So there's a significant difference between 1 and 4, 2 and 4, and 3 and 4. So it would seem like 4 is the outlier, right? 4 is the one that's different because it differs when you compare it to all 3 of the other groups, but you can see that none of those 3 groups differ amongst themselves, right? 1 and 2, 1 and 3, and 2 and 3, no difference between them. So 1, 2, and 3 are all relatively similar, and 4 is the weirdo, right? 4 is the one that's hugely different or significantly different, and it's causing this result, right? It's causing a large F value and a small P value, so we could reject, and then we run the two-key, and we get this, right? So that's how that works. So you can run it in Excel. If it comes back insignificant, good, you're done. If it comes back significant, you're going to have to go rerun it in Vassrstats. So you might want to just get used to how to use Vassrstats because it's pretty darn easy. And then just run everything in Vassrstats. And if it's insignificant, you're done, right? If you fail to reject, you don't have to do anything else. But if it is, then you've already got it there and you can have your two-key results and look at them when you need to. Doing it by hand, this is pointing out what all these things are so you can put them into these formulas. I'm not going to spend any time on that because I don't think any of you are crazy enough to want to do this by hand. There's no real reason why you should. You should kind of take a look at these formulas and just understand where the numbers are coming from and what the formulas are calculating, just so you understand what the numbers are, right? When you get SST total, you know, it's SSG versus SSE. What the hell do those things mean? Well, it's these things. Okay, well, what the hell do these things mean? Oh, okay, well, I can see that it's the sample size minus 1 times the S squared, which is the variance, right? S squared is variance where S is standard deviation. Okay, well, this is the mean of X sub I. So when you go from I to K, that just means you start with the first one, so the mean of the first group, and then you subtract the grand mean from it. You square that, you multiply it by the sample size of that mean, right? So of sample 1. And then you add that to doing the same thing to 2. And then you do it to 3 and to 4. And when you just add them all together, and that's what this thing's doing. So it just kind of helps you see where these numbers are coming from and why you might get a big F value and when you won't. So take some time and look these over and make sure you understand how the formulas work. But for the love of all that is, you know, saying, don't waste your time trying to do these things by hand. That's just torture. Okay, so the MSG is the difference, is the between group MS in the Excel output, and the MSE is the within group MS in Excel output. So if you do this in Excel, that's how you get it, and you can understand what they mean by the things they label them as. And then again, here is the shape. I told you it's not a bell curve. It's like a bell curve that's been pushed, right? Because it always has to be positive, because if you look at the way F is computed, it's a ratio, and those things that make up those ratios are always squared stuff. So you're always getting positive things, right? Squared stuff here and squared stuff there, right? So it's a bunch of positive things added together. So you're always going to get a positive number over a positive number. So F is always going to be a ratio. And so it starts at 0 and then it goes out, and your critical values in your critical area is always out in the tail. It's right, the further you get from 0. And so that's what an F distribution looks like. And that's everything we need to know for Way ANOVA. Don't forget that if you want some more help, go check out my video where I go through a bunch of examples. So if you forgot, my videos are always listed in my weekly announcements. So the Unit 6 announcement right here at the top, I've got a link to a Way ANOVA where I basically talk about the same stuff, just the theory of it, and go through some examples. And then this one, all I do is go through some examples using StatCrunch, which is it's similar to StatKey, only a lot better, and unfortunately you'd have to pay for it, right? So take a look at these for extra help.